So now, if you're running computers to do non-wandering steps, you have to think, and that's extra cost. So people who run computers, they by default see things called attractors, because these are the things that don't blow up your computer. So what's an attractor? You can define some subset of your state space. So for example, your state space allows for temperature of minus 80 Fahrenheit and plus 120, but your climate model only produces something in the range of minus 30 Fahrenheit to 120 or 10 or something. So that's a subset. And if you can prove that you stay here for T, you enter it. So there's some minimal time wherever you started. And then you stay there for all times. You have entered an attractor, an attracting set. So in this big state space, you are in 1,000 dimensions. And it turns out many of them kind of peter out and you find yourself in something smaller. So one thing you can do is, which most of us practice, you can die. So you can, go there and die. Meaning that eventually you're someplace and you don't move in the bottom of some valley. Now, points that don't move, we mentioned them before. For these continuous flows, I insist on calling them equilibria. It'll be clear in Chris's lecture why we need a different word to be a fixed point. So this is a sink. And it has a property that no matter how many dimensions you started, so as a human, your body is a highly dimensional system. Eventually, you end up in 0 dimensions because a point has 0 dimensions. Now, suppose you're alive. So you have your rhythms. You have your cardiac rhythm or breathing rhythm or something, which is periodic, almost periodic, or to good approximation, periodic. And if I, make you run, shoot your adrenaline up, you might go away from your normal regime. And then you will be allowed to come back to rest. And have now an attractor which is periodic orbit. So that's very typical for so-called far from equilibrium systems where, energy is pumped in and it's dissipated. And there is a balance between various forces then. And this kind of biological, chemical, and similar nonlinear clocks are very typical. They're called limit cycles of periodic orbits. And now remember, we were classifying all motions. So that's what we meant by stationary periodic. If you have a attractor, you actually see those things because you end up on them. But then what about everything else? Now, people didn't know for a long time how to think about this. So Lady Cartwright, because this is a quaint, Little Britain custom of knighting people. She was knighted for that. In 1945, while looking at vacuum tubes needed in a war effort for raiders, she and Littlewood discovered what these things can look like. And much later, they were popularized by Edward Lorenz and Hawkins Ruel, etc., who said, this stuff looks strange. So I'm grateful for that name as well. It's a appropriate name, strange attractor. So if you have attracting sets, you can start just by numerical exploration, developing intuitions for different strange attractor for different law. And it turns out this never stops. So there is a graduate thesis basically per one such thing. Is anybody there? Like, say a word.
Word.
This will be a useful notion, but it turns out non-wandering set is much more powerful notion because it allows you to study unstable systems as well, not just stable ones. And you would never be on a second Lagrange point with a Webb telescope if you didn't study those, because second Lagrange point is unstable.